the one. So I will start by I will continue a little bit on what I was talking about last time. So deformations on all their consequences. In fact, these consequences are extremely powerful and extremely fascinating. But my goal today is also to go towards the notion of quantum curves, which means WKB expansion, Schrödinger equations, and things like that. Well, it's not useful to show the screen at the moment, but on the screen you see that starting from topological recursion, I will try to derive a differential equation like Schrödinger equation. And in fact, the goal is to show that topological recursion provides the coefficients in the WKB expansion. And this is something very, very fascinating too. So let me recall a little bit what I mentioned last time. I mentioned that if you are able to compute the derivative of, so if you have a family of spectral curves parameterized by some time, T, and you have a family, and if the derivative of omega 01 is an integral of omega 02, and the derivative of omega 02 is an integral of omega 03, then this is valid for every G on N. This is proved by recursion. Okay. An example was that I developed last time was the following. Take this family of spectral curves that depends some time, where x is just z squared, y is z minus 1/2 of sum of tk plus 2zk. For simplicity here, I assume k strictly larger than 1. Also, all the even values of all the even times, in fact, will play no role. So, so basically, I could even say k larger than 3. Okay, and with the standard B of the complex plane. Okay. What I computed for you last time was that you apply d over dtk, so d over dtk to some omega to let's say omega 01. You found, so what we computed is that the d over dtk of omega 01 was not exactly an integral. Well, a residue is an integral, but we multiply by zk and divide by k. So it's a well, let's call that a generalized integral or an integral on a generalized. In this example, what we had was d over dtk of omega 01 y dx was the integral of let me write it this way. It was a residue is an integral on a small circle. Let me call it C infinity. It's a small circle around infinity. You have infinity in your plane, and you take a small circle around it on the sphere. So we are on the Riemann sphere, P1, which is T with the point at infinity. Okay, and we multiply by 2 pi by 1 over 2 pi I. So let me say 1 over 2 pi I. We also divide by k. This controls C infinity, and we put a measure on it, that k. And then we can write omega 0. So it is not exactly, so basically this is my gamma. Gamma is 1 over 2 pi I k C infinity divided by the measure z. We can call that a generalized cycle.
Does it satisfy properties of cycles?
Somehow, but I'm not going to talk about that now. In fact, this is something that I've been developing over the past few years, this theory of generalized cycles. Not everything is a generalized cycle, but the things that are generalized cycles have an intersection, they form a symplectic space, the intersection is non-degenerate, there is a Lagrangian. Basically, this is something very fascinating, and in fact, these generalized cycles are probably the most fascinating objects. We can discuss that. So somehow, what this says is that deformations are somehow in one-to-one correspondence with generalized cycles. And in some sense, generalized cycles are in, well, it's not a bijection, it's not exactly a bijection, but nearly with the tangent space of the moduli space of spectral curves. So generalized cycles parameterize the tangent space. Okay. Okay. So this is what we had, and using that, we were able to derive that for these curves, for this curve with some t's, we could compute the omega gns at arbitrary t by solving these differential equations in terms of the omega gns of the curve that has no times and whose coefficients of omega gns were the intersection numbers. And this is just a kind of notation. I will come back to that in a moment, but let me now consider another family of spectral curves. So in the second part, so last time I mentioned that this formula is enough to prove Mirza's recursion formula. With this formula, we can prove Mirza's recursion, and I said that in the last few minutes of the last lecture. I want to come back in the second part of this lecture today, after the pause. But I think it would be hard for people who are not familiar with intersection numbers on the algebraic geometry. So I prefer to postpone that to later. But let me now go to another family of spectral curves, and this will bring me towards this notion of wave functions and Schrödinger equations and all that. So now let me consider another family of spectral curve, which is the following. Let's say, in fact, let me again start with the curve, this one, x equals z squared, y equals z, and v is the same. Okay, let me start with that curve again. Okay, and now I want to deform it. And let's now choose. So also let me plot it in the xy plane. It satisfies the equation y squared minus x equals 0. And this is just the square root function. Now let's choose some points. X1, xk, and let's choose some weights. Alpha 1, alpha k. Well, very often I will write alpha 1, x1, alpha k, xk. For those of you who are familiar with the notion of divisors, this is just a set of points with some weights associated to them. The weights could be complex, and the points are points on the Riemann surface CP1, so they are also complex points, but they are really of different nature. They are really of different natures. Also, for people who are familiar with the notion of amplitude, conformal field theories, and all that, somehow I'm going to pick some points with some weights, and I will somehow compute the notion of vertex operator. But let's do that just. So in fact, the idea is that now I want to consider another curve, and this will be my curve S. Let me call it alpha x. Will be a new curve, x equals y equals, and v equals. Well, v is always the same because I'm always on CP1. V will always remain the same, but x and y shall change. And the idea is that now I want a new curve, but such that y has a pole at the x-sides, x1, x2, and so on. And somehow I would like to define a new curve with something like that. Okay, and here, let's say it will be very close to the old curve, except at these new points.
X are real points.
No, this is the complex line somehow.
Okay.
Well, the picture should be drawn in C cross C, which is dimension 4, but I'm not able to draw it on the blackboard. On nobody. Okay. And with such that the residue of a simple pole is alpha I. So basically, I would like to, on that infinity, and I would like that at infinity, my curve continues to behave like square root of x plus O of 1 over x. So y should behave like that, plus or minus. Okay. And I would like that at these points, in this region, I would like that y behaves like 1 over that, like alpha I x minus x I. So if you want the residue of y dx, should be at alpha I at point xi. But only on one of the two branches. I don't want to put the pole on both branches. Otherwise, it would be simple. I would just take y equals, I would just change y to y plus alpha I over x minus xi, and I would put a pole on both branches. I want a pole on only one branch. So let me parameterize that curve as follows. So let me find
residues alpha I xi, right? The residue basically xi.
Yes, so the residue is the coefficient of the pole.
You want
Alpha I. I want alpha I.
So you get alpha I over xi.
No, it's alpha. Okay, we can, let's postpone that. Let me show you what this curve is. The curve is z squared there will be plus something, which means that in fact I have shifted, the branch point is no more at 0, it can be somewhere else. And I do that. Z plus sum from I equals 1 to k. And I want something that has simple poles. So let me take them zeta i's, the values. Zeta I, alpha I. And here, let me call that T1. And what are the constraints? What are the zeta i's on T1? What should they satisfy? The zeta i's are determined such that xi should be equal to zeta I squared plus T1. Okay. And T1 must be equal to sum over I equals 1 to k of alpha I over zeta I. Okay. You see, here I have unknowns, so T1 and the zeta i's are unknown, that makes k plus 1 unknowns, but I have k plus 1 equations to determine them. So in principle, I can compute T1 on all the zeta i's in terms of the alpha i's on x i's.
How did you choose your constraints again? It's just given.
Well, this constraint means that the pole will be at x equals xi. And this constraint is the one that ensures this behavior at infinity. So I have not said it before, I was going to say it now. So this constraint, so we have k plus 1 equations to find the k plus 1 unknowns, T1 on the zeta i's. So how do we find them? We solve this system of equations, and so which means that the zeta i's on T1 can be determined by knowing just the xi's and alpha I. This is a set of algebraic equations. The solution might not be unique, but it's a discrete number of solutions. And typically the ambiguity is that you don't know if you put the pole in the first branch or in the second branch, so you have to choose the solution of your algebraic equation to know where to put it. Let me do the simple example with k equals 1 to start with. So let's start with a simple example, k equals 1. So we introduce only one point. In the language of CFT, we should say that this is the new curve with insertion of vertex operators. So k equals 1. So what is our curve? It's x equals z squared plus t1, but t1 is just alpha 1 over zeta 1. Y is on, let me call it, instead of alpha 1 x1, let me call it alpha on x. Let me remove the 1 index. Z plus alpha over 2 zeta z minus zeta. I will not write the b, okay? It is the same as usual. And let me, on the equations are, so the constraints are that x equals zeta squared plus alpha over zeta. Well, t1 is alpha over zeta. Well, I've already used it here. So you see, this is a third degree equation for zeta. So we have three solutions. At large x or at small alpha, you see that two of them behave like zeta or plus or minus product of x. And there is a third one, which is zeta behaves like alpha over x. Which is an O of alpha. So at small alpha, one of them tends to 0 and two of them tend to plus or minus product of x. Right? Okay, so now I want to apply my deformation formula. And so we have to, so first thing is to compute what is, so I will take deformations with respect to alpha, or not with respect to x. So I want to compute d over d alpha of y dx. And remember, I work at fixed x, and this is subtle, because taking a derivative with respect to alpha at fixed x is not the same thing as taking a derivative with respect to fixed z. Because, in fact, z, remember that here z is square root of x minus alpha over zeta, which depends on alpha. So at fixed x, z is a function of alpha. And so when you take derivatives, you have to take that into account. Which also means that when you write the b is, it seems that it's independent of alpha, but it's not, because z is a function of fixed x. So when we shall compute the derivative of b with respect to alpha, we have to replace z by this and work at fixed x axis, not at fixed z axis. Z, if you want, z is just a dummy variable, parameterize the curve. The actual values are the x and the y. The z's are just, I mean, you could reparameterize z as any function of z, which could also be a function of alpha. It's your right, you can do that, but just make sure that when you compute derivative, you know what you compute. So let me give you the answer. The proof is, well, okay. Just apply chain rules with this, and you will find what I tell you. In fact, there is a trick. If you know this kind of formula enough, it will be. In fact, there is a shortcut, but I don't want to explain it now, but let me just say that this is from infinity to zeta of omega 0. So I integrate the variable z prime from infinity to zeta of z and z prime. This is as simple as that. It's the integral from infinity to zeta. I encourage you to do the computation. So compute the left-hand side by taking derivatives, taking this into account. Compute the right-hand side. You will see they are the same. And moreover, d over d alpha of b of z1, z2, again at fixed x1 and fixed x2 equals, and I encourage you to compute it, integral from z prime equals infinity to zeta of omega 03 of z1, z2, z prime. So basically, our the gamma I was mentioning in the previously for deformations will be the path from infinity to zeta.
Right path.
Sorry.
Does this are closed? I mean, does this depend on the shape of the path? I mean,
we integrate meromorphic forms. So I mean locally holomorphic forms. So it's invariant by homotopic deformations. And here the curve is simply connected, so there is only one homotopic class from infinity to zeta. And so this implies that for every d on n, we have that d over d alpha omega gn z1 zn. Well, and this is for the curve s alpha x of z1 zn equals integral from infinity to so z prime to infinity to zeta of omega gn plus 1 of the same curve s alpha x z1 zn z prime. So now let me it's term of the integration. So it's the case where basically gamma is the path from infinity to zeta. So in fact, since we know the derivatives, let's compute the Taylor expansion. So let me apply this. So Taylor, let me apply this. Compute the following thing: omega gn of the curve s alpha x z1 zn will be I'm just applying the Taylor formula alpha m over n factorial e over d alpha the m of the same thing omega gn of s alpha x z1 zn, but evaluated at alpha equals 0. So which is my initial s. Well, is the derivative, but evaluated at alpha equals 0. Let me write it this way. But now we have a formula to compute the derivatives. And so what does it give? It gives sum from m equals 0 to infinity of alpha to the m over m factorial. Sorry, it's omega gn. So yes, that's right. And what is d over d alpha to the m? Well, we know that when m equals 1, this is this integral. But when you rederive with respect to alpha, in fact, this integration path, it goes in the x variable, it goes from infinity to x, which is independent of alpha. So the integration path itself is independent of alpha. And also taking another derivative, we'll just replace this by a second integral with one more variable, and so on. So what do you get in the end? You get integral from infinity to zeta, repeated m times omega g n plus m. You have your variables. So here now you have the curve alpha equals 0, z1, zn, and then your m variables that are the ones that you integrate here. So this is just the Taylor formula expansion. It is convergent just because, at least, I mean, it is convergence within some radius of convergence, and basically the radius of convergence is when the solution of this singularity starts to have when the solution of the algebraic equation x equals z squared plus alpha over z, alpha over zeta, this equation meets singularity after some alpha. Just because it's an algebraic equation, you will meet. The solution is analytic only in a neighborhood of alpha equals 0, and at a certain point you will meet like a square root singularity. Well, if you want, I'm trying to solve an equation. If I write beta as a function of x, you want to find, you have an equation of a type well, it's a cubic equation, and somehow there are two singular points. Basically, this is the radius of convergence, but I don't want to insist that. Okay, just believe me, there is a finite radius of convergence.
Sorry. So you said that you have several solutions for zeta.
You choose one.
You choose one. So what you say is valid for any of these. Yeah,
yes, exactly. And when you try to analytically continue this solution, at some point you have a problem. Okay. So this is the formula. Let me apply it for the case n equals 0, by the way. And remember that I call that fg. Fg of s alpha x is sum from m equals 0 to infinity alpha to the m over m factorial integral infinity to zeta infinity zeta omega gm. Okay. And I don't know if I introduced to you last time the notion of partition function. The partition function z s alpha x of, in fact, of any curve will be defined as a series. Let me write an h bar. Will be defined, and it's a definition, exponential sum of h bar to the 2g minus 2 f2. I introduced that in the notion of matrix models, and also this is very familiar in string theory and many things. Why is it interesting to look at this series? Well, it's because it satisfies many properties. Indeed, in the matrix models, it corresponds to the partition function, so the matrix integral, and in many other examples, it corresponds to the partition function. So here, first remark, this is a formal series, and now the sum over G does not have a finite radius of convergence. It is typically the FGs grow like 2G factorial. This is a divergent series. To really make sense of that, you should do something like Borel resummation, something like that. or you just consider it as a formal object, as a formal series, like WKB. You can consider it formal, but this object is very interesting. So let's look at what it is for our curve. So for our curve, let me write it this way. So this is our S of alpha x. This is exponential sum from G and N now. H bar to the 2G minus 2 plus N over N factorial integral. All right, so what do we have here? We say that the partition function of the spectral curve where we have introduced these points can be computed from the partition function of the initial spectral curve.
Sorry, here you said alpha equal h bar.
Sorry, alpha Vn h bar to the 2t minus 3. In fact, the interesting thing will be to take alpha equals h bar. So I was going a bit fast. Very often, I will take this as, we define this as the psi function. So it depends on h bar, it depends on our initial curve S, and it depends on alpha x. So again, this is just a notation, but you see, I started with a curve S0, and I define a way to modify it, to introduce a point. It becomes a spectral curve S alpha x, and I can rewrite it as this series in terms of initial S0, and where somehow the x here is computed. And remember that, by the way, remember that when alpha equals 0, zeta is just square root of it. Okay, so now let me go to the next part of the talk, of the lectures, which is this notion of quantum curves and WKB and Schrödinger equation. And what I want to show you now is that this psi satisfies beautiful properties. And in fact, I will take now alpha equals h bar. So let me take psi h bar on some curve, the curve on now h bar x. Okay. Let me rename that h bar to -1, and then we just changing alpha to alpha for h bar. So now I put 1 in my notation. So this is just defined as exponential sum of h bar to the 2g minus 2 plus n over n factorial integral from infinity to square root of x. We get gn. So I was saying, so this is chapter 5. WKB. On number one, we give you an example. A recurve. So which is in fact this example with the curve, which with again the curve x. So which is again x equals z square, y equals z on the usual view. And remember, it satisfies the equation y square minus x equals 0. I will put it in red because it will reappear very soon. Well, let me show you some really. Let's go into the details of the computation because I think this is the best way to really understand how it works. So we have to compute these integrals of omega gns. So first, let's start by, so let me write in this exponential, we have different powers of h bar. What are the possible terms that would correspond to h bar to the power minus, so the lowest possible power is h bar to the minus 2. But first, it would be something like h bar to the minus 2, omega 0, 0, which is what I call f0, but which for the recurve is vanishing. Plus, what are the terms with h bar to the power minus 1? Well, there is only one term with h bar to the power minus 1, which is infinity to square root of x of omega 0, 1. Plus, what are the terms with power h bar to the power 0? It's only the integral of omega 0, 2. And there is a 1 over 2 factorial plus h bar. And here we have two terms. Plus 1 over 6 1. Plus we could have h bar square. And with h bar square we have 1 half of integral of omega 1, 2 plus 1 over 24 omega 0, 4. If you go to h bar cube, that's when we start to have three terms. Yes, sorry, and plus we have also the f2, but which is vanishing. So this one is vanishing. For h bar 3, we would start to have integral of omega 2, 1 plus 1 over 3 over 6 integral omega 1, 3 plus 1 over 5 factorial omega 0, 5 plus and so on. Well, what I just wanted to show you by doing that is that for each power of h bar, there is only a finite number of terms to compute. And they are all the terms that have the sign 2g minus 2 plus n. So if you think of, in terms of geometry, it's all the terms that have the same Euler characteristic. Well, you will see very shortly that in fact this one has a problem. This one has a problem. Just because omega 0, 1 has a pole at infinity. But in fact, when I want to take the exponential of this equation, well, first of all, when I use the d over dt formula, in fact, to get this term, I should have applied it to f0, and I never gave you a definition of f0. In fact, so which means that in fact the formula did not apply to that term. I cheated a little bit. And again, this term comes from the second derivative of f0. And again, I didn't give you the definition of f0. So in fact, these two terms are not really there. I mean, they should be replaced by something else when you take the correct definition of f0. And it just amounts to regularizing the integral. And the thing is that if you change the initial point here, it will just change this by a constant, which means that it just multiplies psi by a constant. Since I will want to study psi up to a multiplicative constant, I could choose any point here, and it's very convenient to choose 0. Now the integral will be converged.
Not a renormalization.
It's just simpler than that. It's just a change. It's just multiplying by a constant.
Infinite.
If you want. No, but if you take the actual definition of f0, you really find this. So basically, my theorem about deformations was not really valid for f0. But I didn't give you the definition of f0. So let's conclude. So first of all, let me define f01, which I already introduced before, is just the integral. It's an integral of omega 01. And so what I mean is that the differential of f01 should be omega 01. So this is y dx. And what is y dx, by the way? Y is z, and dx is 2z dz. This is 2z squared dz. And you recognize that this is the differential of 2/3 of z cubed. In fact, f01 is just 2/3 of z cubed plus possibly a constant. And this is the idea. I choose the constant to be 0. I can also write it as 2/3 of x to the 3/4. Because x was z squared. But written in z, it is a rational function. Written in x, it is multivalued. Just because our curve is a double copy. So in the x-plane, for each x, there are 2 values of z. So you have some let's compute f02. Let's define an f02 such that its derivative is differential with respect to the first variable, and its differential to respect to the second variable would be omega 02. So would be dz1 dz2 over z1 minus z2 to the square. Well, it's very easy to find a function f02 that has this as a double differential, and it's just the log of z1, z2. Log of z1 minus z2 has this property. So when you take the double integral here, you're just evaluating the log at z1 equals square root of x or infinity, and z2 equals square root of x on infinity. But when you do that, of course, you will end up with terms like square root of x minus square root of x, the log of square root of x minus square root of x, or the log of infinity minus infinity. Okay, so it doesn't work. So in fact, when before doing this integration, I will subtract here. I will subtract dx1 dx2 over x1 minus x2 to the square. Which is the fundamental form of second kind, but in the base. Okay, this is just my prescription. What I tell you is that the second derivative of f0 is indeed that. I was again cheating because I never gave you the definition of f0, but this is what you should find. So my f02 here, In fact, in this formula, we can simplify. So what is this log side so far? So this log side is following P. P to the h bar minus 1 to 2/3 of x to the 3/4. Then the next term will be exponentially h bar to the power 0 with 1/2. And we want to compute, sorry. So let me say, so this double integral is in fact, so let me call f02 will be defined for me as log of z1 minus z2 minus log of x1 minus x2, so which is the log of z1 minus z2 or z1 squared minus z2 squared, so which is the log of 1 over z1 plus z2, so which is also minus the log of z1 plus z2. Okay. And here this term should be f02 evaluated as square root of x and square root of x. If I replace this term, this will give exponential minus 1/2 of this log, so it's 1 over square root. So it's 1 over square root. 1 over square root of that, square root of z1 plus z2, which are square root of x plus square root of x, so it's 2 times square root of x. When in fact it's 1 over square root of 2 times x to the power 1/4. X to the power 4, 1. So it's equal to x to the power 1/4. What is the next term? Exponential h bar times. So now it's this omega 11 and omega 03. Let's compute them. I remind you that omega 11 was minus 1 over 16 dz over z to the 4. And let me write it as the differential from f11. And this f11 will be, we first integrate, f11 equals 1 over 48 z3. Am I right? Yes. And I remind you that for this curve, omega 03 was minus 1 over 2, dz1 over z1 square, dz2 over z2 square, dz3 over z3 square. And let me write it as differential d2 of f03, and then which means that f03 is 1/2 of 1 over z1, z2, z3, which is 1 over 2, 1 over square root of x1, x2, x3. This one was 1 over 48 x to the 3/4. Okay, and now what we need here is to evaluate this at all the xi's equal to big X. So what do we have here? We should have f11 of square root of x plus 1 over 6 f03 of square root of x, square root of x, square root of x. Let me replace, so this is 1 over 48. Well, both terms will have x to the So 1 over x to the 3. Here we have 1 over 48 plus 1 over 6 times 1 over 12, 2, so that's 1 over 6 times 2. But and so it's 1 over 48 plus 1 over 12, and I let you compute, but this is 5 over 48. You can play, and the term in h bar square is 5 over 64 x to the minus 3 and 4. So this is the psi that we have computed. Let me call it psi TR, because it's the one we compute from topological. I don't know how familiar you are with WKB expansions and array functions and all that, but you have probably recognized already these questions: 2/3, 3/2, x to the 1/4, 5 over 48, x to the minus 3/2. Those of you who are familiar with that have probably recognized these numbers. This is the beginning of the expansion of the array function. All these terms will exactly correspond to the array function. Okay. Can we check that? So let us try to compute. So if it is the array function is the function that satisfies array second of x equals x times array of x. So this is the array equation. So which means that the second derivative of the function divided by the function should be x. Do we have this property here? We have this property. So let's compute side second over side. Here, by derivative, I mean a derivative respect to dx. It's not a derivative respect to z. You have to not forget the Jacobian when you. Everything is easily written in terms of z, but remember that z is part of x. Take derivative with respect to x. So, and before computing side second over side, let me start by computing side prime over side. Just because it's the derivative of the log of psi. And so this is just the derivative of what we have in the expansion. So this is it. H bar minus 1. The derivative of 2/3 of x to the 3/2, it's easy, it's square root of x. Well, it's a big x. The derivative of the log of x to the minus 1/4 is just minus 1/4, 1 over x. It's the derivative of the log of x to the minus 1/4. Plus h bar times, so here we have 5 over 48 times, well, we have a minus times 3 over 2, and I think same thing as the 5 over 32, and h to the minus 5 plus h bar square, so minus 15 over 64 x to the minus 4 plus 4. Let me call this W. In fact, rather than the Schrödinger equation, I'm going to compute the Riccati equation for those of you who are familiar. And I just observed the following thing, that W prime is psi second over psi minus psi prime square over psi square. Which is psi second over psi minus W squared. So in other words, if I want to compute psi second over psi, I will compute W squared plus W prime. So what it is? What is it then? Let's compute W squared. We have an h bar to the power minus 2 x. The term in h bar to the minus 1 is this times this divided by 2. This times this divided by 2, that makes minus of minus, so h bar minus 1 times 1 over 2 further x. There will be also a term coming from with the power h bar to minus 1 coming from W prime, which is the derivative of that one, which is h bar minus 1, and there will be 1 over 2 further x. Oh, nice. Plus h bar to the power 0. So what is the term with h bar to the power 0? We have here 1 over 16x squared, and we have the first term here, minus 5 over 16x squared. And we have a term coming from the derivative from W prime, which was the derivative of that term, which is plus 1 over 4x squared. And again, 1 minus 5 is a minus 4 over 16, plus 1 over 4, that's 0. And you can continue. On daily, you find that it's 0 to the over. So what did we find? Well, at least empirically, if you compute the first few terms, you find that h bar squared psi second equals psi. This is not exactly the Airy equation. This is the Airy equation rescaled by some factor of h bar. This is very usual to do that, and it's more like a WKB equation. Sorry, it's more like a Schrödinger equation. Schrödinger equation. In fact, this one is the WKB equation. So first, let me tell you what the solution is after the rescaling. X of so psi is in fact the area of h bar to the minus 2/3 x. So this is just what the rescaling is. Second observation is that, let me rewrite this Schrödinger equation in the following way. Let me introduce the operator y hat for the h bar d over dx. Let me rewrite this equation as y hat square minus x applied to psi equals 0. Remember that my initial spectral curve was the curve y square minus x equals 0. So you see that there is it looks very much like each other. The spectral curve, the algebraic spectral curve y square minus x equals 0. And you end up with a differential equation obeyed by psi, which is y hat square minus x psi equals 0.
I should call that P, like momentum.
Yes, you could, but initially it was called y, so I like to call it y hat. But indeed, observe also that this operator has the commutation relation y hat x h bar. So this is why this one is called the curve, the spectral curve. And this one is called the quantum spectral curve. This one is called the quantum Okay. Somehow we have quantized this spectral curve by doing that. Well, this term quantum curve is okay. We can debate a lot about is it a good name to call it quantum curve. People tend to put the word quantum everywhere. Very trendy, I don't know. But so is it totally justified to call it quantum? Okay, this can be re-debated, but basically this is the idea. You have a spectral curve. You would like to find a differential equation with some operator y hat satisfying that, and such that in the h bar going to 0 limit, somehow you recover the classical curve. It can be more subtle because you could find something. So imagine that I would find something like y hat square minus x plus h bar square that equals 0. Something like that. Well, in the limit h bar going to 0, this would still give the same one. The same curve. So basically, it's not so. So this requirement that the limit h bar going to 0 gives the initial curve does not determine a unique quantum curve. What is the recipe to determine a unique quantum curve? Okay. I will not continue with these considerations now, but what I wanted to mention is that if you started with by topological recursion, you automatically get one quantum curve. In fact, you get not only one, because there is this ambiguity. You remember that you had several choices of your equation with zeta, and you in fact get several quantum curves. In fact, it's also because, so in this example, you don't see it, but if you get a polynomial, if you started with a polynomial of x and y, and here you will get a polynomial in x and y hat, there are some ordering issues. And in fact, there can be several quantum curves possible that differ by ordering. And in fact, by choosing the different solutions of topological recursion, you can get them, these different solutions, these different orders. But I don't want to enter more the details now. It's probably a good time for a break. And after I will continue with the Faraday one case.
Maybe there are questions.
It's a good moment for questions.
If we take several values of alpha, then we get more complicated Schrödinger potentials.
Or in fact, this is what I wanted to tell before going to Faraday.
Yeah. I join an appendix to his questions. And where are energies, eigenvalues, or Schrödinger operator?
I think you will see that more in the Faraday case. Okay.
So,
in fact, the X is the notch. Okay.
In this case, you shift X.
It's not visible here, but because in Airy there is almost no parameter. I mean, just by rescaling, you can get rid of H bar and of everything because everything is homogeneous. So somehow you don't see what are the independent parameters in Airy. You see it better when you start looking at more complicated curves. And when you start looking at more complicated curves, you will see that somehow X is the.
So if we try to go in the opposite direction, what is the problem? Like if we just take any Schrödinger equation and then we write the corresponding spectral curve. I mean, we can just take any Schrödinger equation and do the WKB expansion. Will those coefficients satisfy the topological recursion?
The answer is somehow yes. I mean, well, okay. To say a short answer, I would say yes, but there are a lot of details under the carpet when we say this. Yes.
But that's like saying that quantum mechanics is integrable in 1/8.
Well, okay, it's much more simple. So, first thing is that you should not restart from a second order differential equation, but more from a system, linear system. So 2 by 2 matrix equation. So if you do that, then you can indeed find topological recursion. If your system is, let's say, isomandromic.
And it's a linear, so it's first order system of two equations.
In this case, the every system satisfies h bar d over dx of every and every prime is the matrix 0, 1, x, 0, every prime. Let's say psi on h bar psi prime. So under that form, now if you give me a system which has certain properties, then it will work.
But I need to be able to write my Schrodinger equation in this way.
Yes, and the idea is that it's not unique. And somehow you have to choose a gauge. And basically, whether you will obtain topological recursion or not depends on your choice of gauge. Somehow there is always a possible gauge, but you have to specify which gauge. I mean, just starting from the Schrodinger equation has some ambiguity. The idea is that there is a gauge in which the answer will be there. The Parevet equation, let me start by mentioning indeed what happens when we take not one point. Remember my fx, my alpha x. If we take not one point but several points, so let me take 2 points, alpha 1 x1 and alpha 2 x2. And remember, this was x equals z squared plus t1, and now y equals z plus alpha 1 over 2 zeta 1, then minus zeta 1, plus alpha 2 zeta 2, z minus zeta 2, with each xi being equal to z zeta I squared plus t1, and t1 should be equal to alpha 1 over zeta 1 plus alpha 2 over zeta 2. Okay. What is, so, and I just tell you what the result will be for the derivative. Let me choose the case where alpha 2 equals minus alpha 1 equals alpha, sorry. Alpha 1 equals alpha on minus alpha 2. And let me compute the over the alpha of omega gn of that curve. And I will tell you it is the integral from zeta 2 to zeta 1. So, in fact, the partition function of this shifted curve would be, what would be the partition function of this shifted curve? It would be, so the partition function h, and so this shifted curve is alpha x, and let me again put the h bar minus 1 alpha x, will be exponential sum over g on n, h bar 2g minus 2 plus n alpha n over n factorial integral from zeta 2 to zeta 1, zeta 2 to zeta 1, omega gn. Now, zeta 2 is not infinity, so there is no problem with taking integral from infinity. No longer, there is no longer any problem with that. And let me give you what the result is. to the first two orders in H bar, e to the H bar minus 1. So let me take alpha equals 1 now. In terms of, I was talking about vertex operators, but the value alpha equals 1 is the degenerate vertex operator for those who know CFT. It's the degenerate charge. Alpha equals 1. The other charges are not degenerate charges. And basically, you know that it is for degenerate charges in CFT that you will get nice differential equations like GPZ equations. And indeed, that's what we get here. It's only for the degenerate charge that we get a nice equation. So H bar minus 1, integral from zeta 2 to zeta 1 of omega 0, 1, which was 2/3 of zeta 1 to the cube minus 2/3 of zeta 2 to the cube. And remember that Z1, Zi is square root of xi here in my notations. You want x1 to the 3/2 minus x to the 3/2 times. And the next term is 1 over square root of Z1 minus Z2. No, sorry, it's 1 over Z1 minus Z2. Sorry, 1 over Z1 minus Z2. The next term is sorry.
It is what we read on the screen.
Sorry.
It is what we can read on the screen.
Yes. Yes, there is just a small thing here. Yes, basically. Yes, this is that's so. It means that Ricardo should show the screen. Is it visible? So indeed, this is exactly what you have on the screen. So H bar to the 5. It's 5 over 48. Z1 cube minus 1 over 4 Z1 square Z2 plus 1 over 4 Z1 Z2 square minus 5 over 48 Z2 cube plus and so on. So now it's a function of two variables. Let me call it psi of H bar, my initial curve x0 on x1 on x2. Well, let me recall that x1 had a weight +1 and x2 had a weight -1. And this is this formula. There is a very nice property and I give you well the value of this guy is when you compute it in terms of area, and you will see it's very simple expression 1 over x1 minus x2 times the area function of h bar to the 2/3 x1 very prime function of h bar to the 2/3 x2 minus area prime h bar to the 2/3 x1 very prime very of h bar to the 2/3 x2. What is the Berry function? The Berry function is the overall solution to the area equation. And it just corresponds basically to changing h bar to minus h bar. Or it just yes, it also corresponds just to picking the other branch of the square root for the x in the expansion. And so this is really amazing. Sorry, something is wrong here. It says Z1 plus Z2 according to my notations. No, sorry. Yeah, indeed. You see that this quantity has a pole when Z1 equals Z2. So square root of X1 equals square root of X2, but in the same branch. And this seems to have a pole when X1 equals X2. But when they are in the same branch, you have Airy Berry prime minus Airy prime Berry, which is the Vronsky of the two solutions and which is 1. So there is a pole. If X1 equals X2, but in different branches, it means that Berry in the other branch should be Airy. And then you will get Airy prime minus Airy prime, which is 0. In fact, there is no pole when they are when X1 equals X2, but in different branches. So, I mean, it looks like that. And also the array asymptotic as an exponential h bar to the -1 2/3 Z1 cube, and Berry prime as Berry as an exponential with as an asymptotic with the minus the exponential, as I said. Change h bar to minus h bar. So it looks plausible. This can be proved. And this is a general feature. So when you start taking wave functions with more than 1 point, somehow you can re-express them in terms of the wave functions with only 1 point. Or in general, when you introduce many points, you can re-express everything in terms. So this is a integrability here. I will not give you the formula, but okay, I can give you a formula. In general, if you take psi of h bar x0, and you take now x1 with coefficient +1, x2, and so on, plus xk, and then you put minus x tilde 1, minus x tilde 2, minus x tilde k. So in other words, you have 2 k points. K of them have sign +1, k of them have charge -1. The charges 1 and -1 are the degenerate charges. And so you have 2k points. The total charge, so the addition of all charges is 0, and each charge is degenerate, so it's either +1 or -1. So it's like an insertion of several degenerate vertex operators. Then it turns out that this is the determinant of I and j between 1 and k of psi of h bar. This is called Pei identity.
Sorry, could you repeat the condition, the x? The sum equal the sum?
Well, the coefficient of xxi must be either +1 or -1. I mean, the x tildes are just the ones, but with coefficient -1. And you have the same number of plus and the same number of minus. So if you have the same number of plus and the same number of minus, and people would also say supersymmetric, the same number of bosons and fermions.
The Vandermonde in the denominator?
It is included in the definition. It's the F02. It's what the F02 does. The F02 does the Vandermonde. It is. In the usual way of writing Phi identities, you put Vandermonde, but somehow here they are included in my definition by the F02. So this is the general formula. It is satisfied in this Airy curve. The question is it satisfied for every spectral curve? For the moment, this is a conjecture, so it has not been proved yet. The fact that Phi identities is satisfied by every spectral curve. Also, when you do not start with the Airy curve, but with another curve, there are some issues that, okay, somehow this exponential formula here is only what I call the perturbative part. And in fact, to have the phi identity, you need also to include non-perturbative terms. Okay. I don't want to go into that, but morally, this should hold for every spectral curve. For example, with Borrow in 2010, we checked this equation for an arbitrary spectral curve with the perturbative term, with the non-perturbative terms. We checked it up to the third order in each part, but we could not prove it beyond. For arbitrary spectral curves. And now it has also been proved for a very large range of spectral curves, but not yet every spectral.
Is a Hannis curve included?
It should be, but the problem is that it's not clear what psi means for Mirza-Hannis curve. And maybe what is the geometric meaning of that? Nobody knows. Oh no, yes, Mirza-Hannis is not in the cases that have been proved because the curve is not algebraic. But the meaning is not so clear. Also, if you are more in string theory and all that, you could think of this insertion of orthogonal operators. You could also think of them as SZT brackets. Okay, let me now study another example of spectral curve, which would be related to the Palovay-1 equation. So let me start with another spectral curve. So Palovay-1. I don't remember what number it is in my numbering of sections. I think it was Palovay-1. So first, what is the Palovay equation? Well, let me just first tell you what curve I will start with. I will take a curve ST, which will be this one, x squared minus, sorry, x equals z squared minus 2u, y equals z cubed minus 3uz, and g, z1, z2 is the usual one, z1, z2, z1 minus z2 squared. In these lectures, I will never consider anything else. You may recognize like Chebyshev polynomials T2 and T3 for x and y. This is okay. This is also called the 2-3 minimal model. So I labeled ST, but I write the parameter u here. In fact, my relation is that T is minus 3u squared, so u is square root of minus T over 3. Let me consider the case where T is negative. Is real negative, so u is real positive.
Sorry, a question about the phi identity again. This instead in matrix models, I mean, is proven by orthogonal polynomials, and it holds. It's just the determinant formula for all them.
In fact, it holds also in fermionic systems, and it's just it's trivial when you have fermion systems.
Yeah.
Free fermions always obey that. Yes. But not only free. I mean, it can be true even if not free. But
so the point is proving it for spectral curves for which we don't know if there is a matrix model.
Yes. But yes, on this phase, I don't mean in fact integrability. Well, another way to formulate that is that the S matrix of 2k particles is given by the two particles. When you know two particle diffusion, you know n particle diffusion. So it's integrability, and it can be transformed into Hirota equations, into many other equations of integral systems. So let me start by looking at this family of curves. So just observe that you have the equation, so you can eliminate z and write that the equation is y squared equals x cubed plus tx plus 2u cubed. So it's an equation, it's a cubic equation. You would probably think that this is an elliptic curve. But the fact that I can parameterize it with rational fraction means it's a degenerate elliptic curve. It's not a torus, this curve, it's a torus pinched. The curve, topologically, this curve is a pinched torus like that. Just because it's parameterizable by rational fractions, it cannot be elliptic. It's not genus 1, it's genus 0. Well, we shall run topological recursion on this curve.
You say 2, 3 minimal model. What was the previous case?
1, 2. Sorry, it's 3, 2. The other area was 1, 2. In general, if you want to consider a PQ unitary minimal model, you will take the Chebyshev polynomial TQ and TP.
Why you're saying that this is related with the minimal models?
It's a long story. For example, fooling a double scaling limit of matrix models. But just also when you compute the numbers, you realize that it's the same thing as what you would get from the differential equations you get in the end are the Douglas-Schenker correspond to the Douglas-Schenker construction of minimal models. And this is provable. In fact, many of these things are done in details in my book. If you're interested, but especially minimal models. I mean, with Q equals 2. So we shall run topological recursion on that curve, and this is what I will show you now on the board. So we shall run topological recursion on that curve, and what I want to show you is that there will be a differential system associated to that curve. There will be a kind of Schrödinger equation. Naively, you would think that maybe you could replace y by again equals y equals h bar dx, or maybe you will get that y squared hat minus x cubed plus tx plus 2b cubed times psi equals 0. Would it be that equation? The answer is no. That would be a little bit too simple, but nearly. It will be that plus O of h bar. And this O of h bar will be a series in h bar. And in fact, this series will have also poles in x. So there will be a 1 over x minus something. But somehow this is what's called an apparent singularity. It's not really a singularity of a system. And in fact, you can check that psi will not be singular at this point. So it's the notion of apparent singularity. And again, a good way of dealing with apparent singularity is not to write a Schrödinger equation, but a linear system, 2 by 2 linear system, because the 2 by 2 system in a certain gauge is not singular. And that's what it means. Okay. So what makes it look singular is your choice of picture. So before really starting to compute the topological recursion on that curve, let me explain what is the Faraday equation. The Faraday equation is the following equation. You want to find a function u of, so this is a small u, and this will be a big u, and it depends on h bar on time. And you want it to satisfy the following equation: h bar square over 2 d2 over dt square of u minus 3 u square equals t. This is the Pareto-1 equation. We can solve this equation recursively in order of in powers of h bar, and typically to order so when h bar goes to 0, you see that the first term is square root of t over -3, so which is the small u, and this is why I introduced this small u, the first term, plus h bar square times, and here in fact it is in my notebook. Start there. Yes. So you see the next term would be minus h bar square over 4, 3, 2, 8. So the next term would be 1 over 4. Okay. Just compute. Just solve the equation recursively. And u is a sum, so u is a sum over k equals 0 to infinity h bar to the k uk. And with u0, find u. Which is square root. This is the Pareto equation. In fact, there is a way to relate Pareto equation to some integrable system, and let me consider the system of equation h bar d over dx of type on psi tilde. Leave some space here, where we'll add the second column shortly. Okay, let me start by the d over dt, by the way. 0, 1, x plus u 0 psi tilde. And here, this is the big U, the series in h bar. And consider this over d over dt psi tilde. Sorry, d over dx now. And now let me take the more space. So here I will take h bar over 2 u dot. Dot will mean d over dt, and prime will mean d over dx. Okay. U dot x minus u times plus 2u plus h bar square over 2u dot dot. X minus u and minus h bar over 2u dot times psi tilde. It turns out that the condition that these two systems are compatible, they have a common solution, and in fact they have a common full basis of solutions, and this is called the compatibility. The compatibility of these two systems implies that you should satisfy this equation. So if you want, if you take d over dt of that one and d over dx of that one, they should give the same result. This is the compatibility, and this gives an equation of the coefficients, and it gives that. You could also, so how did I find all these coefficients here? You could also think of the following. Try to find a matrix with a polynomial of degree 0 in x, a polynomial of degree 1 in x, polynomial of degree 2 in x, and such that the trace is 0. So here you have to put the opposite of that. Which is compatible to this one. Then it will imply that all the coefficients will take exactly that form on the Pareto equation. So just by fixing the degree 0, 1, 2, 0 will imply this exactly this matrix, and no other matrix. observe that the determinant of this matrix is of degree 3, and it is a 2 by 2 matrix. It is related to this 3, 2 in one model. This is the Douglas-Schenker formulation. You have degree 3 in X and degree order 2.
The compatibility between these two equations is that the matrices commute.
Not exactly. It's the Lax equation. So if I call this matrix V and this matrix R, the compatibility is that V dot minus R prime equals R of V. So it's not. So they do not commute. Their commutator is the derivative. Or if you want written in another way, d over dt minus R commutes with d over dx minus d. You can call that the Lax equation. You can call that the zero curvature. Or the compatibility, I mean, it has many names, but it just amounts to say that the two connections commute. So if you make a big connection in the big space, it is flat connection.
The operators are simultaneously diagonalizable.
No, it's not that. It's really that the two systems have a common solution. The diagonalization, okay, yes, if you want. As operators, they are simultaneously diagonalized. That's right. So it was just to say that the Schrödinger equation is the compatibility condition of that system. So basically, to each, not Schrödinger, sorry, the Palovey-1 equation is the compatibility of this system. And so, which means that to an equation of the Palovey type, usually you can associate the differential system with a certain wave function psi. And this psi satisfies an order 2 differential equation. You can eliminate psi tilde and you can see that psi will satisfy a certain equation. The idea is, which I want to convince you now, that the psi that satisfies the Palovey equation is the same as the psi we compute by topological recursion. So the idea is that this is the same psi. So topological recursion gives us directly the psi. And regarding the question about by the way, about the Schrödinger equation on the energy, if you look at the d over dt system, that's where you receive the energy. Observe that when you solve the dt system, you have that h bar d over dt of psi equals psi tilde. And d over dt of psi tilde is x plus 2u psi. So which means that h bar square d over dt square of psi equals 2u of h bar t plus x psi. And now you see that the energy is x. Right, okay.
I see it, but
2u is the.
I thought that the t was time.
Sorry?
I'm confused.
T is the. Well, okay. I mean, x is just a shift to the potential. And u is the potential. Okay.
U is supposed to be independent of x.
Sorry?
U is independent
Yes.
of x.
Okay. And x is called the spectral parameter. Right. So now let me show you my notebook. I will switch to the notebook. Can you show the notebook?
Ah, sorry.
So you see that this is so when we solve recursively the Palovey equation, this is what we find. So you have here, I don't know if you can see my it works.
Now it's
So the recursive solution to the Paleve one equation gives you u plus h bar square, so h bar 4 and so on. You can compute many. It was just to check that when you compute indeed the h bar square u second over 2, okay, it's just to check that it works. Okay. Now let me run topological recursion. Okay, so we start with our spectral curve. So you see z square minus 2u and z cube minus 3uz on the B. Okay. I'm sorry about the warning messages that some library is not obsolete things. Okay. Ignore that. So we can start computing the omega g ends. That's omega 0,3. That's omega 1,1. Okay, and so on. It's interesting to do on when you integrate, you have f03, f11. Okay, so this is f11 and so on, and you compute all of them. So you should compute also the f01, f02, and so on, and you compute the psi. So you see this is this combination f11 plus 1/6 times f03. Okay. Keep going. This is higher and higher powers of h bar. Okay, you have been to very high powers of h bar. H bar to the 6, H bar to the 7, H bar to the 8, and so on. Okay. These are the FGs. Well, okay, I'm not going to, yes, this is psi. So now, this is the psi we want to consider. Okay. In fact, I started here by computing again. You have 1 point with charge 1 and 1 point with charge -1, and you can compute the psi. But in fact, let me take the case where you have one x with charge 1, and the other x with charge -1, I send it to infinity. That's what I did before. I take intervals from infinity. So you see my package can do that automatically. And so when you do that, you compute the psi. So this is basically the f01, the f02, the f11 plus 1/6 f03, and so on.
Just to make sure, so here you are doing the same construction as you did before by perturbing your.
Yes. Well, I mean, I take the definition of log psi will be always that. Sorry, the definition of psi for every spectral curve will be that. And indeed, it corresponds to the idea that you take your initial spectral curve and you add poles with residues given by the charges. You take your initial curve and you deform it by just adding new singularities that are simple poles with prescribed residues at prescribed points, and you don't want to change the behavior at infinity and all that. So, and basically, there is a unique way of doing that, and it's exactly the one that is here. And so just now, take this as a definition of a wave function for arbitrary spectral curve. You start with any spectral curve you like, and just take this formula as the definition of your wave function. And now compute it, and what I want to convince you about is that if you start with the Paleve curve with this 3-2 minimal model curve, the psi that you get this formula will give you the same psi that was corresponding to the compatibility condition of the Paleve one equation.
I don't understand. How many divisors do you take?
Well, here this could be for arbitrary divisor, but I will specialize it to only 1 point on the infinity. So as I did for every the first case, when I found really every function, it was with I was integrating from infinity to my point. But this would work for any number, and this will satisfy fair identities if you take an arbitrary number. So basically, if you have two k points with k points of charge +1 and k points of charge -1, then this psi will be given by the determinant of one of only the 2-point functions. So let's start by computing log psi. So this is log psi, so the first few orders. So there is the 1 over h bar term, which is just the coefficient is the f01 evaluated at z1 minus the f01 evaluated at z2. You have the log of z1 minus z2 and so on. So this is the case where you have two divisors, where you have 1 point z1 with charge +1 and 1 point z2 with charge -1. But let me now go to the case where you have infinity. Yes, so this is infinity now. So now this is really the log psi, the one I'm talking about, where the integrals are taken from infinity to z. Okay, so exactly the same formula that gave us the area function before. Now we apply it to this curve. And we compute the term with 1 over h bar is the f01. Then we have again this -1 over 2 log of 2z. This is in fact the same factor as before because it came only from the omega 02, so from the log of z1 plus z2 and evaluated at z1 equals z2. Then the h bar term, which is, remember this is f11 plus 1 over 6 f03, compute it, h bar square, h bar cube, and so on. And now I take the derivative of psi, so PS is psi. I take its derivative, multiply by h bar. Sorry, PS is log psi. So this is what I called before the W. What I call PS here is what I called W before, and so it basically is the derivative of the log of psi. And I expand it, and I multiply everything by h bar. So instead of starting with h bar to the -1, now it starts with h bar to the power 0. So the first term is z3 minus 3uz. Oh, recognize this is y. It's not an accident, of course. Well, of course, the term with h bar to -1 was the integral of y dx. So when you take the derivative, you get, of course, y. Completely obvious. The h bar term is 1 over 4z squared. Then you have an h bar square terms and so on, and just expand. Then I want to do again the Riccati trick. So I'm computing this. This notebook is not up to date, sorry, because here it was called, no, sorry. W is indeed the derivative of a log. Okay, that's fine. And I take W square plus h bar W prime, exactly as I did for area. I divide by 2z, which is my Jacobian, because I'm taking derivative respect to z rather than derivative respect to x. Okay, and I compute this series, and this is what you get. So you have a series in h bar. And remember, when we were doing that with area, we found that the leading term was z squared x, okay, and all the other powers of h bar were exactly cancelling. Everything else was cancelling, everything else was disappearing. Here it is not disappearing. Not disappearing. But now let me compute another quantity, which is x minus u, the big U, times h bar second derivative of psi, minus h bar squared psi prime, and everything divided by psi. Which is not exactly this combination A, but A plus something. Basically this U here. Let me compute this quantity instead. And so this is what we have here. And so this quantity, by the way, you see it's x minus u times this A minus, and I just subtract minus h bar w. H bar times psi prime. I just subtract that. So now this is the series I obtain. Since I've multiplied by x minus u, which contains the z square, I get now a polynomial for those z8. linear order, and so on. Okay. And on the right hand side is not okay. So this is what we're finding in the end. So that's what I told you. In the end, what do we find? We find that we don't find this equation. We have other terms with powers of h bar. And the powers of h bar typically contain a 1 over x minus u. Well, okay, I will not go further in that, but just what we find just numerically here by computing these powers of h bar, we find that it satisfies, well, basically, I promise you that the psi that we get by topological recursion is the one that satisfies these equations. This is proved. For example, this is my book, but it has been proved by many other people, many other methods. So in this case of the 3-2 minimal model, everything is proved. I just wanted you to give you a hint. And this is, so what I want to show you is that this is very general. So we start from our spectral curve. And when we run topological recursion, this psi will obey kind of will obey an algebraic equation, which is a deformation of our initial spectral curve. Or if you want, the h bar limit, h bar going to 0 limit of the differential operator that we have here. And when we replace y hat by y, becomes the spectral curve. So this is the case. This is always the case, basically. And moreover, another thing is that we always have this phase identity. So this is the end of this part. So I'm not giving you the proofs. The proofs are quite involved. There are many ways of proving that. And there are two main approaches of how do you prove that psi of topological recursion coincides with the psi of the Pareto equation. How will you prove that? There are two approaches that I call, I don't know, top-down or bottom-up. I don't know. I mean, you go either one way or the other. One way is you start from Pareto equation. You prove that psi has an h-bar expansion, WKB expansion. You prove that order by order it satisfies some equations that are called loop equations. And this implies that the coefficients will have to say the topological recursion. So either you start from the system and you compute it, you show that its h-bar expansion has to satisfy topological recursion, or you can also work in the other way around. You start from topological recursion and you construct the quantum curve. And you prove that what you construct satisfies the quantum curve. The two approaches exist in the literature. Okay, so this is all about quantum curves on integrable systems, but this is, so the summary is that topological recursion has a lot to do with integrable systems. Yes, just another word. So it has a lot of things to do with integrable systems, with tau functions and all that. And on the notion of quantum curve, of quantizing curves. And all this is not yet fully understood at the moment.
Yeah, so if I start from like the Pareto equation, I have some WKB expansion, and okay, I can show that these coefficients in the WKB satisfy topological recursion. But then if we write down the differential equation that gives me the full Pareto equation, not just the WKB, that includes extra information because it includes non-perturbative information. No? And so, yeah, so how can we say, like, let's say we prove that the WKB expansion matches the topological recursion. Then there is a step from going from that to saying, okay, this wave function satisfies this Schrodinger equation. Because that will, if you then manage to solve that equation, you also have the non-perturbative information.
In fact, you can also construct the non-perturbative information directly on the T alpha and the topological recursion side. There is a way to do that. It's a long story, and it's also the present research. Basically, my grant at the moment is exactly on that subject.
It's only for very specific systems.
No, it should be very general.
So basically, it's like saying that topological recursion not only solves the problem perturbatively, but also non-perturbatively.
That's it. And also, yes, another point I wanted to mention about that. When you do things perturbatively, typically the omega GNs or the FGs, they grow like 2G factorial, they say. So all these series in G are not summable. They are divergent series. And this is related to what you just said. Whenever you have divergent series, it means there is a non-perturbative sector hidden somewhere. And can we recover this non-perturbative sector from topological recursion? And the answer is yes. There is a method to do that. Okay, it's really a long story, so I'm going to embark myself on it. So just to say something, topological recursion is the solution to some equations that are called, you can call them Pira-Zero constraints, W algebra constraints, loop equations, Schwinger-Dyson equations. They can take many names, but basically the idea is that topological recursion is really defined as the perturbative solution of these equations. Now, these equations can have many solutions. Your spectral curve, the spectral curve you start with gives you one solution. But in fact, there are many other solutions to the same loop equation. The idea is that the non-perturbative sectors are the other solutions. And but just at looking at the geometry of your curve, in fact, there is a way to know what are the other solutions. And the idea is it can be formulated with these generalized cycles. So somehow, instead of shifting by, instead of using a cycle that goes from infinity to x, let's take a closed cycle. And then you will not change, by doing that, you will not change the behavior at infinity, you will not introduce new poles. We have something that satisfies the same OPE, if you want, the same loop equations, which you can also call Ward identities, and you will have just another solution. And this will be your non-perturbative vector, the instanton. And so basically, you can get every instanton with similar formula. And now, can we reduce the Borel transform and all that? This is precisely what we are working on at the moment. And for example, the work we are doing with Paolo and Alessandro is to apply that to JT Gray.
Because this in general, this non-perturbative completion in general should be unique, right?
Yes, it's not unique. It depends. Well, there are many ways to parameterize it. Some people use Trond series parameters. Okay, there are many. Okay, it's a long story, but indeed it's not unique. But all the information is encoded in the geometry of the spectral curve, and you can recover it by looking at the spectral curve. At least this is under current research. It's not everything is fully understood, especially the Stokes coefficients, but the value of instantons is very clear. In fact, the instantons are all the periods of a spectral curve. So the answer is yes, we can read the non-perturbative completion inside. And in fact, when I said that this psi will satisfy the phi identities, it's only if you take into account the non-perturbative part. It doesn't work if you don't take into account the
Maybe even more general question, like if we have one of these non-perturbative completions, so we have a finite, let's say even for a theory with a matrix model dual, if we have this solution, which is non-perturbative, then it's like we have basically the finite n solution. Then would then be possible to write down like something like these are the original eigenvalues of my matrix. Like at large n, we get some continuous density of eigenvalues, and then we can get correlations. But if we go to finite n, can we say like?
Okay, you have a random matrix, so it does not have a deterministic value for the eigenvalues.
Yeah.
You can compute expectation values of moments or something like that, and you can compute, but you can compute them at finite n.
Okay. So even if we include, okay.
Still random. I mean, you don't have a given matrix. You have a set of matrices with a probability low. So what you can compute is, for example, expectation value of trace of some power, and that has a meaning at finite n.
I agree with that. It's just that people in gravity literature, they try to look for these non-perturbative completions to understand what is really the spectrum of the matrix.
That's usually, well, there are many ways to call that. So the spectrum, for example, in the context of Schrödinger theory, is you want to find what are the values such that psi can be decreasing on both sides of a real axis, for example. With a generic solution to this equation, if you require that it's exponentially decreasing on R plus, because of Stokes homomorphisms on R minus, it could be exponentially growing rather than, if you want that it's decreasing on both sides, it means X cannot be arbitrary. It must take some values, and this is what you call the spectrum. So it's basically some vanishing constraint on the Stokes coefficients or things like that. It's some condition, it's some constraint on the non-perturbative solutions. But so now what you call the spectrum is some, they can be seen as the zeros of some functions. And it's more like, instead of, for example, if you, the analog with random matrices, instead of trying to find eigenvalues of the matrix which is random, which has no meaning, you're more like trying to find the zeros of the orthogonal polynomial, which have more or less the same distribution. For example, the zeros of a Hermite polynomial in the large limit, they look also like the semicircle law. But they have really well-defined values. So zeros of Hn and Hermite polynomials are very precise values.
That's the end.
Yes, we have.
Okay, so thanks.
Just as I said at the beginning of the lecture that maybe I would show the proof of Nirvana's recursion. So if some people want to stay on Tibet, I can do it. I think we can also finish.
You have to go.
Yes, maybe we answer to some questions. If are there any questions in the room or in the virtual room? Questions? Thank you. I don't know. Maybe. Do you feel enough energy for following?
There were a lot of questions over this.
How long would it take?
Not much.
Let's say less than 10 minutes.
Yes.
Okay, so we can go.
Remember that we did every curve with times. Remember that if you started with x equals z squared and y equals z minus 1 x and ck equals zk, we found that omega gn was 2 minus 2g minus n minus 1 gn sum over. So let me start with no times. So without times, we found that this was sum of d1 dn lead space tau d1 tau dn product of tdi plus 1 double factorial zi over zi to the 2di plus 2. Now when we put the times, we found that it corresponds to taking over intersection numbers that correspond to sum of minus 1 half of sum of tk t2k plus 1 tk minus 1 double factorial tau k plus 1. Well, this is in the and the meaning of this exponential is that you should expand it as a Taylor series in VTs. And when you do that, because intersection numbers are non-zero only if the sum of all the degrees is 3g minus 3 plus n, when you expand, you find that each time there is only a finite number of terms in the Taylor expansion that contribute. So in fact, it turns out that it's always a polynomial in the times. Okay, so this is the formula we found. Now, just the trick. The coefficients that you find here are the same as the coefficients that there was in 1, but multiplied by this 2k plus 1 double factorial. So in fact, there is a very easy. So in fact, let me write this guy here as exponential minus sum of t tilde k, well, plus, in fact, sum of t tilde k, tau k plus 1. And let me relate, so the t tilde k's are just the t to k plus 1 times 2k minus 1 double factorial times minus 1. There is an easy way of computing the series of some t tilde k, so let me write it this way. T tilde k minus u to minus k is basically you get it by doing the Laplace transform y dx times minus ux. Because when you do this integration, you see here that you will have something like z to the, so minus 1 half k plus 2 z to the k times 2z dz, that will be this one, z plus 1 dz, times e to the minus u z squared. And you are integrating that from 0 to infinity. And this is the moment of a Gaussian integral. It's non-zero only if k is odd. Okay, sorry. Integrating in x from 0 to infinity means integrating in z from minus infinity to infinity. We go one more. And these moments are non-zero only if k is odd, sorry. So let me replace k by 2k plus 1, 2k minus 1. And a Gaussian integral to z to a 2k will bring a factor 2k plus 1 double factorial. So basically it's doing exactly the job. So let me give you the formula. So let me give you the final formula, which works now for every spectral curve, and which is just an adaptation of this one on just taking into account some powers of 2 in a good way. So let me give you the final formula. Omega gn will be 2 to the 3g minus 3 plus n. I've changed the power, as I said, the powers of 2. Sum of d1 dn exponential sum of t tilde k tau k plus 1 product of tau di g times product from I is 1 to n of, in fact, let me call them d psi di of zi and where xid of z will be the residue at infinity at 0 of b, so z prime goes to 0, we have z prime times z prime to the minus k over k. Sorry, d. 2d plus 1. You can check, but for this b, this is exactly giving this number. So in fact, this is the same quantity. And here the general function of a t theta k, this sum of t theta k u minus k, is 2 square root of pi over u to the, no sorry, 2 u to the 3 of over square root of pi, exponential from 0 to infinity y dx e to the minus ux. So the times that appear, so the cohomology class that appears here is the Laplace transform of y dx. And that makes the formula extremely easy to use. You start from any spectral curve, you compute this Laplace transform, you get the t theta k, and you get your class. Now there is also a formula that, so I don't know if you know the kappa classes. Are you familiar with kappa classes? Okay. So far, I've introduced the tau classes just as a notation. In fact, the nice thing with TR is that you don't need to know anything about classes and so on, or intersection theory. You find it by doing the computation. Basically, TR will tell you all the relations that the tau satisfies. And for example, there are some conjectures about intersection numbers like Pittston relations and all that, and you can find them by TR in a very easy way. And some that were conjectures we put in this way, just by computing residues. So I'm almost done. So this formula now is really very, very general. It works more or less for almost any spectral curve. With any spectral curve. And I just want to finish something, is that every time you have an exponential linear in the t theta case, okay plus 1, there is another way of writing that with what's so-called kappa classes. So the kappa classes are defined precisely by this formula. So it is the definition of kappa classes. Let's call them at k of kappa k. And kappa k is called the Mumford case kappa class. And you see that kappa classes are related to tau classes, just another combination of tau classes. And it's just a combination of tau classes with the t hats are related to the t tildes by just the following formula: sum of t hat k u minus k equals sum of t tilde k u minus k equals exponential of minus sum of t hat k u minus k. Okay. Because this is the formula. So basically the t hat k is just corresponding to taking the log of the series. So I give you some example. You see that t hat 1 equals to t tilde 1, that's the coefficient of u to the power minus 1. T hat 2 or actually the other way around. Minus sum of t hat k u minus k is log of 1 minus sum of t k u minus k. I must have made a mistake. Oh yes, sorry, minus made a mistake. You see that t hat 2 is 1/2 of t tilde 1 the square plus t tilde 2 and so on. So in the end, if you want to write your omega gn in terms of kappa classes, what do you need to do? You compute the Laplace transform, you take its logarithm, and you have your t hats. Now, it's very interesting to do this game with some given spectral curves. For example, let's start with x equals z square and y equals 1/2 pi sine 2 pi z. Compute the Laplace transform, integral of y dx e to the minus ux. So this is the integral of sine 2 pi z over 2 pi 2z dz e to the minus uz square. You see that sine 2 pi z is an exponential, so you complete the square in the exponential. The computation is very easy to do, and in the end, I think we just get minus 2 pi square over u. I think we get that. Well, times square root of pi 3 times u to the 3. I think we get that. As far as I remember, I encourage you to do this computation. So it's a very easy Laplace transform. So it's a very easy Laplace transform to compute. And so remember the rule that I was saying to find the coefficient, the t hat case. Find the t hat case. So you compute the Laplace transform. You multiply by u to the 3/2 divided by square root of pi. So basically, the Laplace transform is just this exponential. But you find the t hat, you take the log of that, minus the log of that. So basically, the t hat, so basically what we get? You get that sum of t hat k u minus k is 2 pi square over u. So basically, you have only t hat 1, which is 2 pi square, and all the other t k's are 0 for k larger than 1. So this is what we find from Nova's curve. The most difficult part of the computation was to integrate the exponential linear in z, exponential quadratic in z. So it's just a Gaussian integration. Just have shift z by 2 pi or something like that. So it's a very easy integral to compute. Then you take the log, which is extremely easy because you get an exponential. And so basically, what do we get? This very general theorem. Just by using, so here I can replace that by case. So by the way, this relationship is due to Arbarello-Tornalba. Probably revisited by myself. It's basically Arbarello-Tornalba. What they write is the series. They expand both sides in the series. Sorry about that. Okay, so where did we arrive? We shall apply now this formula in our case. And what does it give in our case for Mirza? For the curve sine 2 pi z over 2 pi, what do we get? We get that omega gn equals 2 to 3t minus 3 plus n, sum over d1 dn, exponential 2 pi squared kappa 1, product of tau di, product from I equals 1 to n bit psi vi of zi. And this is, it turns out that it is Volter's formula. We've got Peterson form equals to pi square kappa 1. So basically, we have found that if we take the sine, this sine curve, the Mirza-Harnis curve, what we find is the Weil-Peterson form. And this is exactly what Mirza-Harnis was. So what did we get here? By applying this very general theorem to this curve, we find that topological recursion numbers are computing the Weil-Peterson volume. You can play the same game with, let me give you another curve for those who know string theory. Let me take the curve e to the x plus e to the plus fy plus e to the y equals 1. If you know this curve, this is so-called vertex, so this is the mirror of C3 prime F mirror of C3. I don't know if you know that in string theory, this is the mirror curve of the Calabi manifold C3. It's very famous. This is an algebraic curve. So with F belongs to Z, you can compute integral of y dx to the minus ux. It is easy to compute this curve. And in fact, you get the Bernoulli numbers. I think you get I think you get b gamma of u f over gamma of u times f plus 1, simply like that. When you compute it. I think this is what it's worth for this. So you see you have exponentials, you change variables and you recognize the Eynard beta function. So if you do that, you get this product of three gammas. The log of gamma has an asymptotic expansion given by the Stirling formula. So the idea is you take the log of this thing, expand it in terms of gamma, you get the coefficients, and the coefficients are the Bernoulli numbers. Eventually, what you get, you apply the same formula that is here, and your combination of kappa classic by applying the same formula will be exponential sum of Bernoulli numbers e2k over 2k and 2k minus 2, I think, kappa. If you know this is called the Hodge class. Sorry, there is an F. So there is some so there is U, and there is the same with UF, and the same with so times F to the power k plus 1, I think. That's for this one. You would have the same thing with plus F. Minus probably F plus 1, k plus 1. Okay. Because you have one with 1 with F, and one with F, something like that. But it turns out that this is the Hodge class. This is the same thing as Hodge class of F, class of 1, and the Hodge class of minus F minus 1. I'm cheating a lot of details. Maybe this is what Mumford has computed. this very precise combination of kappa classes is the Hodge class. And so if you start from the mirror curve of C3, this formula, so again the same formula by computing just Laplace transforms, gives you that the omega GNs are integrals of triple Hodge class, which is the famous Marino-Werfer formula. Okay, I will.
Sorry, the Hodge class is the right hand side or a lambda? I don't understand.
Lambda is, so this is lambda of f. This one, you see we have an exponential, so it factors into three terms. An exponential of a sum. So it's
Okay,
a-
that
it's a product of
defines
three
the
terms.
lambda.
Each one is a Hodge class.
Okay.
Okay, I won't go. I think it's really enough. But it's just to say that the most difficult part of this computation is to compute the Laplace transform. It's easy. And this provides a very general method. So whenever you have any spectral curve you like, compute Laplace transform, you get some you get some classes, and basically you get a string theory. You construct a string theory by just computing the Laplace transform of your spectrum. And if you have no idea that Hodge classes satisfy certain relations and all that, you will find them by me.
So, okay. That's the end.
The real. It's time to go to lunch.
Okay, so thank you, Bertrand.
Back to lunch. I think we go to lunch.